We considered the channel to be a first order RC filter and qualitatively saw how it behaves. So the input is assumed to be a sequence of digital symbols, either plus or minus 1, and that goes through a transmitter which has a certain pulse shape. We assume this to be rectangular, but you can make it to be something different from a rectangle. So here what we get is the usual picture of the digital sequence, a rectangular digital sequence. And we have the channel. At the other end of the sample, we sample at a rate equal to Ts, which is the symbol period at the input. And the output we get also some discrete time output. Okay. And we also saw that if we can characterize this whole channel very conveniently by looking at the response to a single one, that is a digital impulse. Output, which ideally should be a digital impulse, consists of one main component which we call the cursor and non-zero components before and after. Ideally it should have had only the cursor and all the other non-cursor components should have been 0. And we also defined some terms, everything that comes after the cursor to be post-cursor ISI and everything that comes before to be precursor ISI. And it's named that way because anything that comes after affects the symbols that are transmitted afterwards. Anything that comes before affects the symbols that are transmitted before the current symbol. And you can affect the previous symbols because you have a delay in the system. So if the delay is more than one symbol, you can affect the previous symbol, previously transmitted. Okay. So this is, you can think of this as, this is the response to a single pulse. So this is like the impulse response, a digital impulse response. So if you have any other signal here, let's say something, let's say this is X of n, and let's say this response I have drawn here is H of n. What is the response to X of n? It's a convolution between the sequence and the impulse response. It's this with the sum running over n. So what you do, you know how to do convolution, right? You flip the sequence and then basically you flip the sequence and sum over all of the parts. So let's say this is the input sequence 0, 1, 2, 3, and we are interested in the output at symbol 1. And we assume that the response looks something like this. And then we have to flip this. So all of the post-cursor ISI comes to this side. So that means the symbol 1, the main part of it gets multiplied by this, and the previous symbol gets multiplied by this, and that also affects symbol 1. The one before that gets multiplied by this and also affects symbol 1 and so on. All of these affect the symbols that are following. And if you had something here, then this is symbol 2 affecting symbol 1. So that is the precursor. So it's just the impulse response, that's all. Okay. So let's first look at some frequency characteristics of this. This is a continuous time channel. This you can think of as going from discrete to continuous time. And here you go from continuous to discrete time. So how can you represent the effect of this? What is the effect of this? What I mean is how can you represent the effect of this block quantitatively in let's say the frequency domain. So it is taking a single pulse and holding it for a certain period. So what is it is a sample and hold. Okay. And what is the transfer function of the sample and hold? It is a sink. Or 1 minus e to the minus st, that also works out to be a sink. So in this case, let's assume this is the response to a single pulse. Okay. So basically this is the impulse response of this part. It is taking you from discrete time to continuous time, but that doesn't matter. And the frequency response of this is, what is the response of this? If you think of this as a continuous time impulse response, it's the area times sink of the height times ds. Okay. Or the width times ds. So it is, so what does it look like? At 0 it will be the area. So yeah, if you assume this is 1, it is. So how much is it? Minus j pi ts. So j2 pi times ts by 2. That's correct. So it has some phase as well because it is delayed with respect to time equal to 0. What does the magnitude response look like? Same, but yeah, it goes to 0 at integer multiples of fs. That's the main characteristic of it. So this is 1 over ts, this is 2 over ts, and so on. So this is the shape of the sink. We are multiplying it by ts. It doesn't have any energy at 1 over ts. How come? So it has. Why does it have nulls at 1 over ts, 2 over ts, and so on? What does the Fourier transform mean? Like, what does the Fourier transform mean to you? What is the Fourier transform? Yeah, it is frequency composition. So what does it mean? Any signal can be represented as a sum of sinusoids, and the relative strengths of sinusoids are given by the Fourier transform. And in case of continuous frequency variable, you have infinitesimally spaced stuff, so you have to integrate it, not sum it, but that's a detail. So this means that the amplitude of the sinusoid at fs, 2fs and so on are 0. How do you calculate the Fourier transform? So the Fourier transform is you take every sine wave and you see the amplitude, you multiply it by the signal and then integrate it. Okay, that gives you the best RMS fit amplitude or something. That is you minimize the mean square error between a signal and the sum of sinusoids, and the resulting sequence that you get is the Fourier transform. Are you familiar with this? You try to fit a sine wave to any signal and you minimize the mean square error in the process. That is, you minimize what you are fitting minus what is really there, the whole square. That, and now the variable that you have is the amplitude and the phase of the sinusoid. And once you minimize that with respect to the amplitude and phase, the resulting amplitude and phase is the Fourier transform. Okay. So take a sinusoid of any phase, which is an integer multiple of fs. You will have one full cycle and the integral will be 0. You take a pulse and you can take a full cycle like this or with any other phase, the integral will turn out to be 0. And the same holds for harmonics of fs also. Because if you hold a waveform constant for Ts, then you multiply it with the sinusoid whose frequency is fs and integrate it, you will always get 0. So this, it turns out, has important implications on clock recovery, because the clock that you want has a frequency of fs, and that is precisely the frequency that is missing from the data. So you will have some difficulty recovering the clock from the data. Let's say the clock is not given to you. You are supposed to look at the data and then find out the clock. Now, from this Fourier transform, it looks like the clock frequency is precisely where the frequency content is, the spectral energy is minimum. Okay. So we'll see that part later. And the reason why it is 0 can be seen quite clearly. You calculate the Fourier transform or the Fourier series by multiplying the signal with the sinusoids and then integrating it and so on. So you take a sinusoid at fs and integrate it, multiply it with any phase and integrate it, you will still get 0. Okay. Because you are integrating over a full cycle of the sinusoid. Certain response of the transmitter, P of f, in this case we assumed it to be a rectangle, but as I have mentioned before, the transmit response need not be a rectangular pulse, it can be something else also. And let's say the response of the channel is certain h of f. So the response between this point and this point is what? The response of the channel is h, the response of the transmitter is p. What is the total response? P times h. Now this is the Fourier transform of the impulse response, continuous time impulse response between these 2 points. Now if you send in a discrete impulse and then sample at the output and look at the output, what do you get? How do you get the response between these two in terms of P of f, h of f? P of h of f sampled at Ts. The combined impulse response is sampled at Ts, which means that this P times h is aliased with a spacing of 1 over Ts. So P of f, I'll just draw the magnitude of P of f. That looks something like this. It is sin x by x. And h of f can be anything. We'll see some examples now. So let's say h of f is some low pass filter. This one still has nulls, but the combined response will be something of this sort. And then you alias this with the spacing of fs to get the overall response. And what do you want the overall response to be? So in the time domain, we want the response to be a single impulse and all others being 0. So in the frequency domain, we want it to be flat. Okay? Not changing with frequency. So essentially that is one way of thinking about this whole problem. If you want to transmit data without any intersymbol interference, then this combined impulse response should be flat in the frequency domain. The overall discrete time response is aliased P of f, h of f, and in case of an ideal channel, it will be constant. So what happens in reality is this h of f can be severely low pass, in which case the alias response will not be flat and you will have intersymbol interference. So I will come back to this switching between frequency and time domain afterwards. But again, we will go back to our simple example of RC filter and see what happens in the time domain. Okay. But now we understand what happens. We have the transmitter, which is usually a rectangular pulse or gives you a sync response, and we have the channel h of f. And if we had an ideal channel, h is 1. If not, it will have typically a low pass response, but it could have some kind of magnitude response that is not constant with frequency. Okay. And we have sampling at the end of it. So we'll have aliasing also. So anything that we have to do, so this is the channel, anything that we have to do to improve the quality of transmission, meaning reduce the intersymbol interference and so on, can be done on this side or on this side. We'll see how each of them affects the response. Okay. Any questions on this? Why do we have to sum over infinite number? What is the reason? No, that's because of sampling, right? This is more of a mathematical operation. Like once you sample it, you are sampling over infinite number of copies. It's not like, it is not related to the bandwidth. Once you sample some signal, you are doing the summation over infinite number. I mean, at least that's how you get the result mathematically. Doesn't mean it will take you infinite time to do it. It's not something that is happening over time, right? It's not some summation that's happening as a sequence of summations of two terms or something. It's just the effect of sampling can be represented as an infinite summation. Oh, no, this is in after sampling you will have it in discrete time, okay? So it is always repetitive. Discrete time response always repeats at the sampling rate. What does the low pass mean? So this corresponds to Fs. I mean, if you remember the large omega, which is omega times Ts, okay? And this is Fs by 2. So in case of a discrete time signal, a low pass signal means some signal whose frequency is somewhere here and a very high frequency. The highest frequency that's possible is pi, right? That is the alternating sequence. If you have plus 1, minus 1, plus 1, minus 1, it has a frequency of pi radians per sample, or half if you remove the radian. And this is a high frequency. Okay? So if you have a discrete time frequency response which is like this, where this is Fs, this is a low pass channel. Okay? I mean, this is also low frequency. This is the same as DC. But this whole part is redundant. You can only look at this and judge whether it is high pass or low pass. So let's go back to our example of an RC, because we can calculate the result in time domain. We can also get some insight into what happens when you have intersymbol interference. So again, we look at the response to a single pulse. This goes through a rectangular pulse shaping. So the input is like this. The output, depending on the RC corner and the pulse width, will be something of this sort. And the samples of this will be at these points. The first one will be 0, the second one will be some positive value, and everything will be positive if you have a single RC. The sampled version of this is what I call the impulse response H. What is the equation for H? What is the value of the first sample? What is the value of the first sample? This is the response to a single pulse. This is 0, okay? At n equal to 0. At n equal to 1, what is the value? 1 minus e to the minus Ts by Rc. Yeah. It is 0 for n less than or equal to 0. And for n equal to 1, what is it? It is 1 minus e to the minus Ts by Rc. And for n greater than 1, yeah, n minus 1 Ts by Rc. See, this is the initial condition. The value at n equal to 1 is the initial condition, and it decays as e to the minus T by Rc. And that you have to sample at Ts. So this you get to be 1 minus e to the minus Ts by Rc and e to the minus n minus 1 Ts by Rc. Okay. In fact, the same equation can be used for n equal to 1 also, because the multiplying factor is unity for n equal to 1. So the response of this is 1 minus e to the minus T by Rc e to the minus n minus 1 T by Rc. Now this is just the exponential that you get from an RC filter. I apply a pulse. It first follows 1 minus e to the minus T by Rc, and then when it falls with that initial condition. And the whole thing can be represented by this single equation. So in fact, if you look at it, this looks like of the form for n of 1, 2, 3. I consider this. So it's 1 minus e to the minus T by Rc. For the second one, it is, and for the third, it is. So let's just take some typical cases and see. So what we are trying to do here is to see what is the bandwidth we need from the channel. What do you guess would be the bandwidth that you need from the channel? So let's say the channel is low pass and it is first order. What is the bandwidth you want? You don't want any attenuation at all, so it is twice of this. Of course, if you keep on increasing the bandwidth, you will not get any attenuation, so it can be anything more also. Can it be lower than twice of this? How would you figure out? Okay, at the instant n equal to 1. N equal to 2 and 3. So basically you calculate this. We are halfway there. In fact, I didn't first explain why we are doing this, but we are doing it to see what is the right bandwidth to use. Okay. So we would calculate the sequence, and then we'll see, we'll kind of define where we can neglect all the intersymbol interference terms, right, compared to the cursor, and that is the bandwidth that we want. So what is that value? What is your guess? Okay, let's look at it. First, let's take a case where e to the minus t by RC is 0.1. Okay, so I have just the reason I take it is because all these are simply multiples of e to the minus t by RC, right? So it's very easy to calculate. So what is the cursor value? 0.9. What is the first? 0.09. It's 0.1 minus 0.01. Okay, and what is the third one? It's 0.01 minus 0.001. And in case of the RC stuff, it goes as it goes with an exponential decay. That is the response of the RC. Okay, so in fact we can neglect it after this. So this actually looks like a usable channel because the cursor is 0.9 and the first one is 10% of that, and the second one is 1% of that. And after that we can definitely neglect everything. And what is the bandwidth corresponding to this? What is the bandwidth of the RC filter in terms of the data rate fs? In this case, RC ln 10. So that is what? That is the time constant, or rather TS is RC ln 10, or the bandwidth of the RC filter is 1 over 2 pi RC, okay, which is what? Ln 10 by 2 pi times fs. And how much is this? Approximately 1/3, right? So this is 2.3, this is 2, I will cancel that off, and pi is 3. So even for fs by 3, we don't have such a bad situation. So we don't really need 2 times fs. And typically, if you have about 75% of fs, you don't have any problems with intersymbol interference. Okay. So that's the rule of thumb. Now this is a first order filter. So this affects the response in some way. You can have a high order filter with the same bandwidth, and it will affect the response in a different way. So fs by 3 may not always be sufficient, but you can see that the bandwidth that you need is some fraction of fs. Okay. How can we say whether ISI is good enough or not? So that again we'll see, but for now take it that this is good enough. And also you can see that the numbers are exponentially dropping off, right? The next one will be 0.0009 and so on. So basically after the first one, and definitely after the first two, you can neglect everything. So exactly how we can neglect it, we'll see. So some fraction of fs is the bandwidth that you need, and if you have that much bandwidth, you don't have to do anything else. So if you have bandwidth less than that, you may have to do something at the transmitter or the receiver so that you can receive the signal properly. Okay. So let's take a few more cases. So first I take e to the minus ts by RC to be 0.1. Instead of specifying the value of RC, I will do this because it's easy to calculate. Okay. So the first one is 0.1, the second one is 0.09, 0.0009 and so on. Okay. Let's say I take this to be 0.25. What happens? First one is 0.7, 0.1875 probably. That is. The next one is approximately 0.05. And let's take a more extreme case where e to the minus ts by RC is half. Okay. So what do you observe here? If I plot this, the first one, the cursor is here, and the next and the next, and after that it's practically negligible. Okay. So if I take the next one, what happens? So what happens is the amplitude of the cursor keeps on reducing, and the amplitude of the post cursor keeps on increasing. So you have a certain energy injected into the channel, and that gets spread out over a longer time. Okay. That's what happens here. And this is typically what happens as we lower the bandwidth. So the amplitude of the cursor reduces, and the amplitude of the intersymbol interference elements increases. Okay. So that's why you start having more and more problems with intersymbol interference. Okay. Now this we derived for an RC filter, but this is true in general. Okay. As you reduce the bandwidth of the channel, the cursor amplitude reduces. So the amount of signal you have to detect reduces. Not only that, the intersymbol interference increases. Let's say our discrete time channel is described by lecture10, and the cursor is h of 0, and we drive this with a plus minus 1 sequence. So for plus 1, what do you receive at the output? What are the possible values that you can receive? See, if h of n equal to 1 for n equal to 0 and 0 for this, then of course whatever you feed in, you get out. So what I am asking now is, what do you receive when you have, let's say, random input data, and the input data can have either plus 1 or minus 1. What is it that you receive at the output? In general, the response is h. What is it that you receive at the output? So it's the convolution of H with the input sequence. So what you receive naturally is H of n convolved with X of n. What is the largest positive input that you can get from this? Sum of all the H. Yeah. So absolute value, because some elements of H of n can be positive, some can be negative. But the highest you receive is when the ones that are positive are weighted with +1, the ones that are negative are weighted with -1. So this is the largest thing that you receive. Let's say the value of the X corresponding to H of 0 is 1. What is the worst analog value that you receive? Meaning you are supposed to receive a 1. Basically in this convolution, the value of X that is multiplying H of 0 is +1. But the sum has to, what I am asking you for is the sum such that all of the ISI is in the worst case. It is H of 0 minus and n not equal to 0, H of n. So you have arranged all the other input bits so that the ISI is maximized. So output, let's say, is H of 0 X of 0 plus H of 1 X of -1, so on. Also, you can have precursor ISI. Now this product is 1. That's what I have said. Okay. By definition, in fact, I'll take. In fact, the product is not 1. X of 0 is 1. So the transmitted symbol is 1, and all of this represents the intersymbol interference. I want to maximize this intersymbol interference. What do I do? For those values of H where it is positive, I use this to be -1, and for those which is negative, I use +1. So that way a maximum amount is subtracted from the first term. Okay, that's how I maximize the ISI. So this gives us some kind of quantitative idea of how much the ISI should be, right, for error-free transmission. What should it be? Firstly, of course, this sum of the absolute values of H of n for n not equal to 0 must be less than H of 0. Otherwise, you simply get negative values when you send a positive value. Okay. In reality, so this whole thing must be greater than 0 by a sufficient amount, and that sufficient amount depends on the amount of noise that is added. Okay. So the signal to noise ratio should be calculated from this value, this worst case value. So that gives us an idea of how much ISI we can tolerate. So if it's more than that, we have to do something so that we can get back to this condition. Okay. And of course, if the second part of this, the summation is more than H of 0, then you get a severe case of errors. So then even without noise, you get errors. So if you have some random input sequence corresponding to a 1, if there was no ISI, you will receive H of 0. In case of ISI, depending on the bits before and after the desired symbol, you get something less than H of 0 and also something more than H of 0. The minimum value is H of 0 minus summation of this magnitude for n not equal to 0, and the maximum value is the similar one, whereas this is plus. Okay. And here I have assumed that H of 0 itself is 0. So sorry, H of 0 itself is greater than 0. H of 0 is positive. Okay. So this is the value you wanted to receive for a symbol 1, but you receive a range of values, and you have to make sure that the minimum value is sufficiently above 0 for the given amount of noise. So let's say the impulse response was just H of 0. Okay. There was no ISI. Then in response to 1, you will get H of 0, and there is no intersymbol interference. But then let's say we add the remaining parts of H of n to the response. So now we have intersymbol interference. So now corresponding to a +1 symbol that was transmitted, you get something, you could get something less than H of 0, you could also get something more than H of 0. The minimum value is H of 0 minus this part, and this should be sufficiently above 0 so that it overcomes noise and gives you the desired bit error rate for error-free transmission. So if that's the case, you don't have to do anything. But if that's not the case, which frequently turns out to be in practice, you have to do something so that the overall response, including whatever you add at the receiver and whatever you add at the transmitter, satisfies this condition. Just clear what ISI does? It reduces the amplitude that you receive for a given symbol, and that how much it reduces depends on the impulse response, because the bit pattern is random, so they can add up in various ways, and it's quite possible that they add up in a way that is worst case, right? In this case, for instance, it's assumed that the input pattern has exactly the right signs to create maximum interference, maximum intersymbol interference. So let's go back one step. What we saw was, as the bandwidth of the channel reduces, the value of h of 0 reduces, and value of h of n in this particular case, at least the magnitude of h of n for n not equal to 0 increases. So what does it mean? What does it mean for this term? It keeps reducing, because the first part keeps reducing and this part keeps increasing. So that's why as you reduce the bandwidth of the channel, you get more and more intersymbol interference, and you have a higher probability of error. So let's say it's an infinite bandwidth channel, that is h of f equal to 1 for all frequencies. So then what do you get? What you want is not the h of f times p of f to be constant, but the alias h of f times p of f to be constant. So let's say h is 1 for all frequencies. So you have this sinks. I am drawing only the magnitude, and then the alias version of this is something like this. So will this be constant or not? It's actually easy to see it in the time domain. The time domain is, you have a rect like this, and then you sample this every ts. So you get only a single one and all others to be zeros. So you get the ideal value. So it's not p of f times h of f, but the alias function of that. So as the bandwidth keeps on increasing, it does get better, because it won't disturb the shape of the sink. So in this case, h of f is 1 for all frequencies. So I can think of it as it is, these things are getting added. Now let's imagine some h which has a large bandwidth, but not infinite. Okay. So some of these higher order lobes will get attenuated. Okay. So the sum will get disturbed slightly, right? But then if h of f becomes smaller than fs, some significantly smaller fraction of fs, then you will have something like this that affects the main lobe itself. Then the summation is severely affected. So as you increase the bandwidth, it will get better.